Okay, so let's get started. So last time, the last thing we discussed, well, okay, what are the things that we discussed are uh, the fact that, so the main thing that we proved was the fact that the exponential map creates some diffeomorphism, specifically like a bijection between some open neighborhood of 0. Okay, what did I exclude? Okay, so between an open neighborhood of 0 in the Lie algebra and an open neighborhood of the identity in the group. So if I would like pictorially, maybe if I draw a new picture here for the last lecture. So we have the exponential map that goes from the Lie algebra, which is really a vector space, the Lie group G, okay? And it maps 0 to the identity element of the group. And the main claim was that the exponential map provides a bijection, a continuous bijection with a continuous inverse. In fact, it's differentiable with a differentiable inverse. So it comes to the diffeomorphism of a neighborhood of 0 in the Lie algebra and a neighborhood of the identity in the group. It's not true that the exponential map creates a diffeomorphism between the Lie algebra and the Lie group. We have seen that it might not even be surjective. Okay. And in the case, it might not even be injective as well, say in the case of the circle. If you consider your Lie group to be S1, the circle, it's a Lie group, it's a matrix Lie group, just like matrices of like the sort of rotation matrices, so to speak. And the exponential map would be the map that takes any t. If I can get these things away from what I'm drawing, it maps a matrix like a t to e to the it. So if you see that like points which are of the form 2 pi ik are mapped to the same thing, to the identity element. So it sort of wraps around this line around the circle. So it's not an injective map. All right. But at least locally, things are good. So now let me see. There's a question. Mahan, are there any topological conditions to guarantee the X with a global diffeomorphism? The conditions are usually not topological, Mahan. The conditions are maybe sometimes more algebraic. So for instance, we have the well, for nilpotent Lie groups, for nilpotent Lie algebras, the corresponding Lie group will have the property that the exponential map is a global diffeomorphism. So if your Lie group is nilpotent, then its Lie algebra will be nilpotent, and then X will be diffeomorphism. That's a standard fact. Then we have the class of solvable Lie algebras and solvable Lie groups, and the exponential map is not always a diffeomorphism there, but there's the so-called class of exponential solvable Lie algebras and solvable Lie groups, for which the X is a diffeomorphism. They're called exponential. And if I am not wrong, as long as okay, so I have to state it correct. So I mean, yeah, for if you get your solvable Lie algebra in some way as rational points of some solvable algebraic group, I think, in some proper way, then you get an exceptional solvable group. So yeah, the conditions are more algebraic. And the thing is that this maybe the most useful version would be for the nilpotent ones, the one that's used a lot in analysis, in harmonic analysis, so to speak, say harmonic analysis on the Heisenberg group and so on. No, that's the exponent. That's the like bijectivity or like a global diffeomorphism of X for the nilpotent case. So that's the most useful one. For exponential ones, it is somewhat useful if you want to try to understand representation, like unitary representations of solvable Lie groups. But maybe the sort of more interesting class of objects in the world of Lie groups are the reductive ones, which are kind of opposite to being solvable. They're the ones with the fact that the solvable radical is the center. You've seen a lot of examples of them. These are like matrix Lie groups that I described, the orthogonal, the ones that preserve isometries. GLN and SLN, in addition, and the orthogonal, unitary, so on, symplectic. So they are examples of reductive Lie groups. And for those, the exponential map, as we have seen, is rarely a bijection. So it turns out, yeah, it becomes somehow a not so useful fact in that world. Okay, so let's continue. Thanks for asking this. Any other questions from here? So last time we were trying to finish this argument that any element of a connected matrix Lie group can be written as a product of exponentials. Okay. So let's go to the next page. Let me create a new page. Okay. So I don't know. Maybe I should write the statement again. Or should I just show this? So maybe okay. So proof. Okay. Maybe I'll just show it and then then I prove it. So this is the assertion, the corollary that we want to prove. G is a connected matrix Lie group, and we want to show that every G can be written as a product of exponentials. Okay. So as you remember from last time, the idea was to look at these sort of ratios of gamma values for a path that connects the identity to G, and you want this ratio to somehow be small so that you can express this ratio as an exponential. And then you get a bunch of points. You choose a bunch of points so that these ratios are small, and every factor becomes an exponential. So this last thing is a product of these factors. All right. So I'll just make this more precise on the next slide, on the next page. So proof of corollary from last time. So I want to express this proof, like explain this proof in a number of steps. Maybe, I mean, there's 4 steps. But maybe I first explain step 3, and then I'll tell you what the other steps are. And this is usually how we try to like write proofs, right? I mean, first we try to figure out what we need, and then sometimes what we need will be the first step, because the order of things should be sort of a logical order, okay? So what do we want? So, I mean, remember that we start this, so choose, so given G, in the connected Lie group G, choose a path gamma, a continuous path, basically, that connects the identity element to the element G. Okay, so here's the picture. So this is the image of the path, okay? So now, if you remember, we wanted this ratio to be small. So this gamma S, gamma T inverse, so to speak. Gamma S over T, but I mean, factoring of matrices doesn't make sense. So I would like to write it as this, okay? I want this to be close to the identity. So how can I control the Hilbert-Schmidt norm of this guy? What I can do is I can try to factor out a gamma T on the right, gamma T inverse on the right. So I can write this as gamma S minus gamma T times gamma T inverse, okay? And now the norm is a multiplicative norm. The Hilbert-Schmidt norm is multiplicative. So this is less than or equal to norm gamma S minus gamma T times norm gamma T inverse. So now if we can show that for S and T sufficiently close to each other in the interval 0, 1, both this quantity and this quantity are controllable. And in fact, we want to show that this is very small and this one cannot be too large, then you're done. Then this difference, gamma S, gamma T inverse minus I, will be small and it will be an exponential. That like this guy will be an exponential. Okay, is it all good? So let's see how we can do this. Well, how can we control this guy, norm of gamma T inverse? Well, it's the inverse of the matrix gamma T, so maybe we should control the norm of gamma T from below somehow. Okay, so how can we do that? Well, yeah, any suggestion? So this is norm of gamma T as T varies in the interval 0, 1. What's the property of the interval 0, 1 that we've been using? It's compact. Therefore, any continuous function on that will have bounded norm. And in fact, this norm will be away from 0 because the image is compact and it cannot contain 0 as its limit. Okay, because it's contained in GLNC. So this means that the norm of gamma T inverse is less than or equal to M for some positive M for all T in 0, 1. Okay, the existence of the T is guaranteed by the fact that the interval is compact. Okay, and the second thing is that this quantity, gamma S minus gamma T, gets small when S and T becomes sufficiently close. And that was a consequence of, pardon? Uniform continuity. So uniform continuity, any continuous function on a compact set is uniformly continuous, okay? So uniform continuity of gamma implies that there exists some epsilon, or maybe I should say for every epsilon, there exists a delta. For every epsilon, there exists a delta such that if S and T are in 0, 1, maybe I write it as a quantifier sentence for all S and T in 0, 1. If their difference is less than delta, then norm gamma S minus gamma T, maybe I should just remove this and draw it somewhere else, okay? Is less than, no, I can say less than epsilon, but I really want the product of these guys to be less than some epsilon. Maybe I could say less than epsilon over m. Okay, I've already chosen some m, okay? So now I see that this is less than epsilon over m times m, which is epsilon, okay? So this holds. So step 3, so this holds for all S and T in the interval 0, 1. So for all S and T, such that, okay, so I forgot, such that, maybe I should remove these guys too. The absolute value of S minus T is less than delta. Okay, so now if I choose epsilon, say less than log 2 or whatever, I mean less than some quantity. So if epsilon, so maybe I should step 4. If epsilon is chosen such that the epsilon neighborhood of I, the identity in G, is in the image of the X map, and this we can do because X gives it the diffeomorphism onto some open neighborhood of the identity, right? So there is some radius epsilon which fits into the image. Okay, so then we have the following, that for all S and T in 0, 1, if the absolute value of S minus T is less than delta, then we should say for the corresponding delta, corresponding abbreviated delta, we have, if this holds, if S minus T is less than delta, then gamma S gamma T inverse, which now lies within a good, sufficiently small neighborhood of identity, will be e to the x for some x in the Lie algebra, okay? Because it's in the image of the exponential map, so it's e to the x for some x, okay? Okay, so if I take 2 points on this curve that are images of, say, T1 and T2, such that T1 minus T2 is less than delta, then gamma T1, gamma T2 inverse, or gamma T2, gamma T1 inverse is exponential of something, okay? So now I just choose a bunch of points like T1, T2, T3, up to Tn. So now finally, choose 0 equals T0, I don't know, then less than T1, less than Tn equals 1, such that Ti plus 1 minus Ti has absolute value less than delta. Okay, so then gamma Ti plus 1, gamma Ti is inverse is e to the xi for some xi in the Lie algebra, and hence gamma Tn can be written as e to the x1. Yeah, maybe I should write it as like, maybe it's e to the xn. It's e to the xn gamma of Tn minus 1, which is e to the xn minus 1 gamma of Tn minus 2 which is e to the xn e to the x1, where x1 to xn are in the Lie algebra. Okay, is it clear? Everybody happy with this argument? Pardon? Any questions?
Yeah, is there an algorithm for computing this except for computing the constellation like that?
to write an element as an product of exponentials, you really need to know how to compute the inverse image of the x, right? So yes, depending on the group you work with, if you can write an explicit formula for the logarithm. For the reductive groups and for like many of these matrix groups, you can explicitly write formulas, right? If your group is given by some nice, maybe the condition would be if the group is algebraic by some reasonable condition, then maybe you can do that. Yeah, definitely for these examples, you can do this. Yeah. Any other questions? So if there are no questions, I'd like to shift gears slightly and talk about representations of Lie groups and Lie algebras. Okay. So a representation of a Lie group or Lie algebra is nothing but a homomorphism into this GLV Lie group or Lie algebra corresponding. So the definition is let G be a matrix Lie group, a finite dimensional. So you can consider infinite dimensional representations as well, but let's not do that in this course. So because of space issues, I write finite dimensional in this abbreviated way. So finite dimensional complex or real, so this will be clear later, representation of G is a Lie group homomorphism I going from G to GLV, where V is a either complex or a real vector space. You guys don't see this nicely. I'm sorry. I mean, okay. Okay, it's a complex or real. Okay, I mean, when I say a vector space, okay, I mean a finite dimension. Okay, and as usual in module theory, so okay, I mean, so we denote representations. Okay, maybe I don't need to write it, so I may just say this. So I mean, so now a representation is usually denoted by this pair pi v. Pi is the homomorphism and v is the vector space on which it acts. So pi would be mapped from G to GLV. Okay, and by the way, GLV, just to be clear, so GLV, if V is a complex vector space of finite dimension, then it's just Cn for some n, and GLV is just a GLNC. And if V is real, then V is Rn for some n, and GLV means GLNR. And by n, real matrices of invertible, which are invertible. Okay? So now, a representation is noted by this pair pi V, and as usual in model theory, we call a representation faithful if there's no kernel. So we say pi V is a faithful representation if the kernel of pi is the identity. Identity, sorry. Yes.
Silly question. So for the
There is no silly question. Yeah.
for the non-congenial V, because in the textbook, because GLV is defined as the invertible linear transformations of V, because the all the invertible matrices can be seen as linear transformation.
Exactly. It's
So
like
we
if
can
for a vector
identify-
space, you choose the basis, and when you write that matrix of that linear transformation in that basis, you get the matrix.
I
And
think-
then basically you get, the composition of linear transformations is just multiplication of matrices, right? This is the standard linear algebra. This is what matrices were designed for. This is the reason the reason they were invented.
So whether
Yeah.
like whenever we're giving a GLV, we can just consider it as GLNC or GLNR.
That's right, depending on the context. But it's easier most of the time to work with GLV because it simplifies the notation. Okay. Now we can also consider representations of a Lie algebra. So for the Lie algebra, it's just the same. It's just that the capital GLV becomes lowercase GLV. Okay. So maybe I just give a remark. The definition of a representation of a Lie algebra G is almost the same. So we just replace GLV by GLV, which is isomorphic to either GLNR or GLNC. Maybe I write it like this. For this Lie algebra of n by n matrices with the usual matrix commutator, okay? And pi going from this Lie algebra this time into GLV is a Lie algebra homomorphism, which means it's a linear map that preserves the bracket. The bracket of two things, the Lie bracket of two things in G under pi will be the Lie bracket in GLV, which is like xy minus yx. It's sort of a commutator, standard matrix commutator. Any questions so far? All is good? All right. So maybe okay, maybe I give one more definition and then I give some examples. A subspace W of V is called invariant. It's called invariant. So it could be either G or like either G invariant or G invariant, depending if you walk like if you want a group representation or a Lie algebra representation. If I don't know, is it a good way to write it? Okay, if pi G W is contained in W for all G in G, or respectively G in the Lie algebra. Okay, maybe I should just write the condition again. Respectively, pi x W is contained W. So if you're talking about the Lie group representation, the condition for invariance would be this for all G and G. And if it's for Lie algebra representation, it's essentially the same thing, but this time the argument comes from the Lie algebra. Okay, so now you see that previously when I talked about the derivative of a Lie group homomorphism into G, like in general, like not just into GLV, I use capital phi and lowercase phi. Here I'm abusing my notation. I'm using pi for the same thing. Maybe strictly speaking, I should have used capital pi and lowercase pi. Okay, for maybe this would be more appropriate for the group ones and this for the Lie algebra ones. But nobody really does that because I mean, some people maybe use pi for the Lie group representations and d pi for the Lie algebra, but then things become kind of messy if you want to use a lot of d pi's. So some people just don't do it and just say it's we abuse the notation. Okay. All right. So now let's do some examples. Maybe I want to give one more definition. So I defined invariance, and now we say pi v is irreducible. We say it's an irreducible representation if it's only, if the only, maybe I should say, if the only invariant, either capital G or lowercase g, I mean, depending on the context, the only invariant subspaces of V are the zero subspace, the trivial ones. Okay. There are no other invariant subspace. So let's do some examples. So let's take, say, G to be R. And let's take V, say, to be C2. And I would like to give an example of a representation of G on C2. So I define pi going from G into GL of V, which you know is just GL2C, right? And we've kind of done this before. So pi is like a map from R, I mean, into GL2C. How can we realize R as a matrix Lie group, really as 2 by 2 matrices rather now? Well, pi of T is the matrix 1T01. You can easily see that this is a Lie group homomorphism. It's a group homomorphism. It's easy, like, you know, you could easily like see by matrix multiplication that pi s plus t equals pi s pi t, and continuity is clear because the entries of this matrix are continuous functions in the parameter t. Okay, is it all clear, Mahan? Jenny, are you good? Okay. Yeah. Well, I could put the entry here. That's a good question. I could put the entry here. It would still be okay, but I couldn't put the entry here because then if I multiply two matrices like T001 and like SST here, you see, then I get product. I don't get the sum. Okay, that was specifically designed to get the sum. From product of matrices, I need the sum of numbers. Okay, thanks for asking this question. This is an important point. Might not be totally clear. In fact, I mean, once you know this example, maybe it's now trivial, but I mean, if you're just asked, like, how do you realize R as a matrix Lie group? It's not, I mean, you really have to think about it. You can't realize it as 1 by 1 matrices. You really have to go to 2 by 2 matrices. Okay? All right, and continuity is clear. Now, is it irreducible? Are there any subspaces of C2 other than the trivial and everything that are invariant under this?
Okay, yeah, I don't know what to put. 0 in the first coordinate and whatever you want in the second.
Kind of maybe the other way around. You put everything in the first coordinate. So if you think about, so if you set W to be CE1, which means like vectors of the form, and I write them in column form, vectors of the form 1, like, I don't know. I don't want to use T, maybe I should say X0, where X is in C. Then this matrix, so I mean, then maybe we should do the calculation. So pi T times X0 is 1t01 times x0, and you obtain x0 again. In fact, everything is pointwise fixed. We didn't even need that. We just needed to be stay like this to stay inside W, and it does. Okay, so this W is a proper invariant subspace. Hence, pi V is not irreducible. Okay. Any questions? Are there any other irreducible? Are there any other invariant subspaces? Do you think those? Huh?
I don't think so.
Any suggestions? Any proof of this fact, maybe? Can you prove that there are no other invariant subspaces?
If you have a non-zero in the second coordinate, maybe you can do something like that. You can get it.
Yeah, you can do a direct examination. Like, what are the possibilities for subspace? You have a two-dimensional space. All the subspaces are like either 0, 1, or two-dimensional. So you have then you have to look for like a proper subspace will be one-dimensional. So it will be some scalar multiple of some vector. So if say vectors of the form xv for a given vector like v1, v2. And now you can check when you multiply by these matrices, the way the entries change, that the only way it can be a scalar multiple of itself is that you have a 0 in the second coordinate. Okay, so that's just by direct examination. That's a simple exercise. Okay, but there's no like linear algebra exercise. Okay, so there are no other invariant subspaces. So a lot of times, a lot of things in mathematics, not generally, not in Lie theory, but in general mathematics, can be related to a representation of a Lie group or a Lie algebra. And then in order to understand that representation, it's best to understand the irreducible factors. So you might want to find, maybe if life is good, you might be able to describe this vector space as a direct sum of irreducible representations. That will be like the best you can hope for. Most of the time that doesn't happen. Even in this example, you can't hope to describe like V as a direct sum of irreducible subspaces. Then you should hope for like obtaining a composition series and getting information from the composition series. Okay, so let's look at another example. By the way, one thing I wanted to emphasize is that, well, we could also think about C2 as R4. Okay, so this could have been a representation of R on a four-dimensional real vector space. But if it was R4, I would have mentioned it, either V as a real vector space, or I would have written as R4. Okay, now if you want to understand subspaces or sub-representations, so to speak, of a given representation, if you start with a complex representation, the subspaces are conventionally considered complex subspaces. And if you start from real ones, you can consider real subspaces. Okay, so we don't usually look at, well, okay, if we want to work with real subspaces of a complex representation, we should stipulate that this is a realified version, which means like you forget the complex structure on the vector space. You think about it as a real vector space. Okay, so now here's another example. So as you see, the Lie group doesn't have to be a complex Lie group, but the vector space can be complex, and we will only look at complex invariant subspaces. Now here's another example. Let's take G to be GL2R, 2 by 2 real matrices, invertible. And let's take V again to be C2, and this time again pi goes from G to GLV, which is GL2C. And so pi of X is just X as a linear transformation on C. Okay, I mean you can any real matrix can be thought of as a complex matrix, so it defines a complex linear transformation on C2. Okay, so now is V irreducible or not? No. Okay, so here's the thing. So we can take W to be R2 as a subspace of C2, and clearly this is G invariant. But are we allowed to do this? Not if we stipulated that we're working with a complex representation. Okay, So in other words, as a complex representation, so pi v as a complex representation it is irreducible. It's not difficult to see that that's the case. The only complex subspaces that are kept invariant by this GL2R are the zero and everything. There is no one-dimensional subspace that's invariant. Okay? I mean, if such a subspace existed, it means all real matrices have a common eigenvector, which is nonsense. Okay? But pi v as a real representation is reducible. Since W equal to R2 is G invariant. Okay, all is good? Now here is one more definition, which is fundamental to representation theory. And again, that's part of the picture that if you have some algebraic objects, the next thing you want to consider between them is morphism. So you have to define maps between representations, okay? And so that's the next definition. So let pi and sigma be two representations of the matrix Lie group G. So we assume that they're both real or both complex. Okay, we don't want one real and the other one complex. Okay. Now, an intertwining map from V to W is a linear map. Now, linear means either R linear or C linear, depending on the context. If you're in the real co-representation world, you want R linear. If you're in the complex world, you want C linear. Okay, so it's a C linear map that commutes with the actions, which means that T pi GV equals sigma G TV for all G in G and V in V. So the picture is that you have V and you have W and you have V and you have W, and this T is a map in the horizontal direction in this direction, and like in both rows. And now you have pi G here and you have sigma G here. So pi G is a map from V to V, sigma G is a map from W to W. And this assertion, this relation really means that this diagram commutes. If you go this, it's the same as you go this. Okay, everybody happy so far? So now if you have a bijective intertwining map, you call it an isomorphism. So a bijective. Intertwining map is called an isomorphism between two representations. And so we usually write pi v like isomorphic to sigma w, like this, if such a t exists. And of course, like isomorphisms between representations create equivalence classes. I mean, each class of isomorphisms is an equivalence class. And yeah, and we would like to understand representations up to equivalence. That's the right way to do it, of course, right? So now a sort of rewarding of the theorem, which stated that a Lie group homomorphism corresponds to the Lie algebra homomorphism and vice versa, the uniqueness part, is the following proposition. So let G be a matrix Lie group. And let G be the Lie algebra of capital G. Now let V be a vector space, of course, finite dimension, over R or C, depending on our choice. Okay. And let pi from G to GLV be a representation, Lie group representation of G. Okay. So then there exists a unique derivative. So there exists a unique representation Well, the book uses pi underline, which is fine, but that's really not common. Into GLV, such that pi e to the x is e to the pi underline x for all x in G. And this is immediate. This is really a special case of that previous proposition. Yeah. Now here is something which is okay, good to know and not a consequence of the previous proposition, but anyway. So here's another fact about like trying to relate irreducible representations of capital G and lowercase g, fracture G. Okay. So it turns out that irreducible representations of the two are really the same once you assume that capital G is connected. Okay. So let G be a connected matrix Lie group. So let G be the Lie algebra of capital G, and also let pi from G to GLV be a representation of G. Okay. So the first is that pi is irreducible if and only if. So I write IFF. If means if and only if, okay? If and only if pi underline going from G to GLV is irreducible. Yeah. And the second claim is that okay, so this is not stated properly here the way I wanted. Okay, so let sigma again from G to GLW be another representation of G. Then pi is isomorphic to sigma if and only if pi underline is isomorphic to sigma underline. So to understand representations of a Lie group at the level up to isomorphism, for a connected Lie group, it suffices to understand the representation of the Lie algebra up to isomorphism. Okay, so this basically reduces a lot of questions about Lie group representations to linear algebra. Okay, it's like a Lie algebra representation is just a linear map, and invariance like irreducibility or like so on is just or isomorphism is really some questions in linear algebra. They're all formulatable as like linear transformations. So it's some complicated problem in linear algebra that you have to solve. It doesn't mean it's always trivial, but that's just what it is. It's just Lie algebra, linear algebra. Okay. Well, you can say the whole mathematics is set theory, but okay. All right, so let's prove this assertion. So first of all, for the first part, so one direction is easier. That if maybe okay. Actually, maybe I prove the second statement first. This is the way I outlined the proof here, so it looks a bit like it's easier to do the second one and then somehow use the idea for the first one. So let's prove the second one. All right. So suppose that pi is isomorphic to sigma. So what this means is that there exists P that goes from V to W isomorphism of vector spaces, okay? Such that T pi G equals sigma G T for all G and G. It's an intertwining operator. So there's a bijective intertwining operator, okay? So now how do you get to some intertwining operator at the Lie algebra level? What trick do you use? It's a standard trick we've done before. Huh? Yeah. So this is like for G in G, I want something for like X coming from the Lie algebra. Something easier maybe. How do we get Lie algebra elements from Lie group elements?
Look at the image, and if we're connected, we're connected. So we can look at the whatever.
Yeah, this direction doesn't need connectedness. The other direction does. So I mean, the algebra elements are just the tangents to this e to the tx, right? These exponential maps. So why don't we plug in e to the tx here? So then this means that t pi e to the tx equals sigma e to the tx t for all in R. And so now, by the definition of the pi underline and sigma underline, so this is t e to the pi underline at like maybe I should write t pi underline x is e to the t sigma underline x t for all t. And then what do I do? And as usual in this course, differentiate at 0. So, I mean, like, I don't know, it's like, I remember there was a joke when I was an undergrad, and anytime we couldn't solve a problem, we had a friend who said, just differentiate at some point. So, And most of the time, such a trick works. So anyway, so here you see that this kind of trick works. So, all right. So when you differentiate d dt at t equal to 0, so we get t under, and so when you differentiate respect to t is linear, right? Now you basically use again multi-linear, like multivariable calculus. You differentiate such a thing, you just have to take the derivative of the thing after the linear transformation because this t is constant. Okay, so you end up with pi underline x times e to the 0 times pi underline x because you set t equal to 0. And on the other side, you end up with sigma underline xt. Okay, so hence t will be this intertwining operator for between sigma and pi. Maybe I should write pi and sigma first. Okay, pi underline is isomorphic to sigma underline via t. Now you more or less can reverse the arrows. Let me explain how you can do that. So conversely, if pi underline is isomorphic to sigma underline, so then we have a t going from V to W, which is an isomorphism of vector spaces, not as modules yet, but I mean for like G, but for certainly algebra, yes. So such that T pi underline X equals sigma underline XT for all X in G. So now what do we do? How do we relate it to the group elements? So the first thing I want to show is that I can exponentiate this to at least a one parameter subgroup corresponding to that. The step one is to show that t pi e to the tx equals sigma e to the tx t for all t in R. Why can I do that? So this is a little bit tricky. You know, basically what I want to do is I want to really write something like, this is like pi of 1 plus tx plus t squared. So I want to write something like this. Pi of 1 plus tx plus t squared x squared over 2 factorial plus t cubed x cubed over 3 factorial. Okay? And I want to say that this is equal to the sum of like a I want to say this is like the sum of sigma pi underline x to the power k t to the k over k factorial. And then use this relation, use this relation iteratively to get some relation between pi underline x to the k and sigma underline to the k. And then add all of those relations. Okay, really, this is the idea. This is one way to do it, and you can then, kind of bother yourself with the proof of convergence of everything. So you have to really prove that a lot of things converge. Okay, or you can be sketchy and say, okay, this is a proof, and delay and sort of declare victory. Or you can just you can be sort of fastidious and say, oh, I really need to prove things, and then you have to fill up pages and pages. Now here's a simpler kind of argument once you make some assumptions. Okay, so I want to explain another argument which is kind of shorter, with the assumption that you know ODE, but unfortunately that assumption is false, right? Okay, but at least, okay, I will prove this using this false assumption. How about that? Okay, so let's continue with this false assumption, but I'll explain the thing that you don't know. Okay, so let's consider, so we consider gamma 1t to be the left-hand side, which is t pi e to the tx. Okay. Oops. Where did I get the CC here? Okay. Ah, I know I'm erasing everything. Okay. So now let's differentiate this in general. So I mean, first of all, what is gamma 1, 0? Gamma 1, 0 is t. Okay. And what about the derivative of this gamma 1 at the general value? So you end up with t. And when you differentiate this thing, now you can write pi underline x e to the power, well, there's a t, okay, so e to the power, what happened? Did I stop the share? Sorry about that, okay. All right, so now I guess we're back, hopefully. All right, okay. So if I differentiate this, I get pi underline x e to the power, or maybe just pi 1. Pi e to the tx. Okay, because I can write this pi 1. I think I'm suppressing the pi 1. Sorry, there's no pi 1. There's a pi. Okay. Okay. So I mean, I'm writing this as e to the t pi underline x, and I'm differentiating at general t. Okay, t is not 0 anymore. Okay, but what I see here, well, I can let this go past. Okay, so what I obtain is pi underline x times t pi e to the tx, which is pi underline x gamma 1t. Okay, so this means that gamma 1 satisfies, so maybe I should say conclusion. Gamma 1 satisfies the differential equation gamma 1 prime t equals t gamma 1 t. Okay, and by a similar calculation, if I set, if we set gamma 2t to be the right hand side here, which is this guy, sigma e to the txt, again, gamma 2 0 is t, and gamma 2 prime t satisfies the same differential equation. Okay. Now, the fundamental theorem of ODE says that you have a differential equation with an initial value. There's a unique solution. Okay, there can't be more than one solution. Okay, so from fundamental theorem of ODEs, it follows that the solution to the equation gamma of t equals gamma t prime equals t gamma t is unique. In particular, gamma 1t equals gamma 2t for all t. Okay. I mean, this uniqueness, where does it come from? I mean, maybe I can roughly explain the idea. Suppose you have this kind of equation. Well, these are matrices, but if they were not matrices and just numbers, you could think about this as gamma prime t over gamma t equals t. Okay. But now, how could you write the left-hand side? Does anybody know what this is, left-hand side? That's right. This is the log gamma t prime, right? Okay, so now the derivative of something being constant, yes, pardon? Let me see. So log gamma t prime, yeah, that's in principle what it is. So now the derivative being constant, it will tell you what this is. This is just some linear, like some linear map. Okay. I mean, then you will know uniqueness of this gamma. I mean, so it basically tells you that the solution is an exponential. Okay. I mean, maybe the right way to say this would have been to take a ratio of gamma 1 over gamma 2, but anyway, that's just the idea. Okay. Oops. Okay. And now, so this completes the proof of the second part of this assertion. And for the first part, the idea is the same. So maybe I just briefly explain. For the first part, so for the first part, you want to show that capital G invariance and Lie algebra invariance are the same thing as long as capital G is connected. Okay. I didn't finish the proof of the second part. I have only proved this. Okay, you should have reminded me. I only proved this. I only proved this. And I haven't used connectedness. You should have told me where is connectedness. Okay. So I just proved this relation, which means with respect to elements which are exponentials, elements from the group which are exponentials. But then what do? Why do I have this relation for all elements of the group? Exactly, as product of exponential. So then this will be the second step, okay? So step 2, since G is connected, so here connectedness is used, right? Any G in G can be written as e to the x1, e to the xn, xi is in G. So now step 1, used iteratively. Yields T I G equals maybe I just write T pi, okay, T pi G, which is T pi e to the x1 e to the xn equals sigma e to the x1 sigma e to the xn T, which is sigma G T. Okay. So this completes the proof eventually. And now for the second part, for really the first part. Okay, so the first part, what was the first part? That capital G invariance and Lie algebra invariance are the same. So first of all, so W, if W is G invariant, then clearly it is also G invariant. The argument is really the same as the proof of the first direction in part 2. So if you know pi G, so okay, maybe I don't know, maybe I should say something about it here. So if pi G W is contained in W for all G in G, well, you can just take exponentials. And then again, by differentiation, at t equal to 0, you get this pi underline x W is contained in W. Okay. And conversely, if pi underline x W is contained in W for all x in G, so then, well, pi underline x to the power k W is contained in W, and then you could just look at this sum, sigma pi. I mean, this now, you know, the convergence issues are a little bit less complicated. All right. But now this left-hand side is just e to the power underline, which is just pi to the x. So basically you obtain pi e to the x W is contained in W for all X in G. And then again, using the fact that any element of capital G can be written as a product of exponentials, you obtain that W is capital G invariant. Okay, all is good? Everybody following and happy? Now, okay, so here's one also important observation. We have been looking at a real algebra, a representation of a real algebra on a complex vector space, right? That was part of our setup. But we can always complexify this action to get a representation of the complexification of G on a complex vector space, which is kind of better because if it's better to work with everything complex vector spaces rather than partly real, partly complex vector spaces. So here's the assertion. So here's proposition. So let G be a real algebra, and let pi going from G to GLV be a representation. I abbreviate representation to repen of G, oops, lowercase g, on a complex vector space. Okay, so then pi has a unique extension to a representation. I denoted by pi sub c. Maybe I write it here. It goes from GC to GLV again. The target doesn't change because it was already a complex vector space. Here, GC is just the tensor product of G with complex numbers over R. This really is like G plus square root of minus 1G. As a vector space, that's what it is, okay? Defined, so this pi c is defined by the way you expect it. So pi c of x plus square root minus 1y is just pi x plus square root of minus 1 pi y. On the target space, you already know V is a complex vector space. So this is a complex Lie algebra. So this multiplication by minus I doesn't require any extra complexification in the target space. You don't want to tensor this with C over R anymore. There's already a C acting there. But on the domain, you have. Okay, you have to do this extension. Okay, so this basically is a way to do transition between complex representations of real algebras to complex representations of complex algebras. Because, most of the time we think about everything being complex. How much time we have? We have only a little bit of time. Maybe I just remind you of the following example. If G is the matrix Lie group, and if fracture G is the Lie algebra of G, then we have the representation, which is this adjoint representation we should talk about. Last time I called it an adjoint representation. Maybe I called it adjoint homomorphism. I forget. Maybe I used adjoint representation. But we hadn't defined representations before. Now it's clear why it's called an adjoint representation, okay? This goes from capital G to GL of G, where at G of X is just a GXG inverse, right? And we have seen before that add underline of x is
Little add that.
the little add x, which is the bracket. Okay, maybe it's a point to kind of stop. So next time, what I would like to do is I'd like to talk about representations of the Lie algebra, like the Lie group SU2. Okay, this is the simplest sort of non-trivial example. Okay, so our next goal, maybe I briefly outline this next goal. Study representations of SU2, which by now, by the exercises you've done in the assignment, you know it's basically the set of matrices of the form alpha, beta, minus beta bar, alpha bar. With alpha and beta in C, alpha plus beta is 1. Okay, so you did SU11. This is not exactly what you did in the assignment, but I mean, you can compute this based on what you studied, but not in the assignment. Sorry, this is almost the assignment, not exactly. In the assignment, you really did SU11. Okay, which is isomorphic to SL2R. This is now SU2, but we have done this example before. This is this kind of matrices, and I would like to describe all of the irreducible representations of this compact Lie group. Every finite dimensional representation will then be a direct sum of these building blocks. So this is what we will do next time. And we realize these representations on spaces of polynomials of different degree, homogeneous polynomials of different degree. It turns out that for any dimension, for any positive dimension, there is a unique irreducible representation of that positive dimension. And we will construct that representation. And this is one of the most fundamental facts in Lie theory. I mean, this is something everybody who does anything related to tangentially to representation theory, Lie theory, they should know this by heart. Okay, are there any questions? Okay, if not, then we will continue with this on Wednesday. So please study what I talked about today about representations, because next time I will use this heavily. The next lecture will depend on understanding of the today's lecture heavily. So please study and be prepared for the next lecture.